you.
And the more irritated they get, the worse it's going to be when they actually do get into your system. They have to face everything.
Sometimes
That's
not even
funny.
face, sometimes just completely blown away.
Yep.
Let's just delete the server or fork files.
Yes.
Long story short,
Don't piss off the red team.
don't piss off red team because they're better than you.
We made that mistake. We went from first to fourth in nationals because we got red team to run a virus. They saw an executable file on our website, which they were sent to that executable file because they had triggered some heuristics saying that they were a malicious user. Of course, they downloaded it and ran it on their personal laptop.
Oh.
Colorful ponies started dancing around the screen joyfully over everything. Despite the instructions that we gave on how to remove this, they could not figure it out. We got 0 points for our red team score, dropping us from first place at nationals by a margin to fourth place. Don't annoy red team. Beat them, but don't try and give them viruses. Is that
Don't try and give them viruses.
Okay, we're going to get started. Today we have Ben Holland, who is currently doing research at DARPA.
Yep. So actually, I'm doing my research at Iowa State for them. So it's minor distinction. Anyway, so this talk is called A Bug or Malware. You'll see references to DerbyCon because these are the DerbyCon slides that I presented at DerbyCon just 2 weeks ago. You can not see the presentation online because there was no audio, but I'm trying to add audio back in. So anyway, this is the same talk but with audio, so you guys get to actually see the talk. Okay, so I had always wanted to introduce myself through a command shell. So this was my attempt to do it, and I actually set up a whole VM just for this. So who am I? I'm Ben Holland. I'm a member of Iowa State University. I presented this talk with Dr. Kathari, but he's not here today. We are not at DerbyCon, and the talk at DerbyCon was supposed to be a mix of 3 tracks. There's a break it track, a fix it track, and a teach it track. And this talk was classified under all 3. So that's what this talk tries to do, although not necessarily in that order. Finally, the talk is called A Bug or Malware, and a few disclaimers. Parts of this work were funded by DARPA, but this talk does not reflect the views or opinions of any agency of the U.S. government or Iowa State University. Everything I say here is my opinion, and aside from that, hello world. So let's get started. Okay, so a little background. What was this project? So DARPA has this program. They have this problem. The Department of Defense wants to outsource contracting, development of applications, programs, and just general software, right? They don't want to have to write the software for every single thing that they do. They want to be able to buy a printer and not have to audit the software on the printer, right? Because who knows what the printer's doing. And we've seen attacks where printers actually phone home, or they make copies, or they're used to run Metasploit against your network. So what they wanted to do was fund a bunch of teams, mostly universities and business, to come up with a solution where once they receive some source code from a business or a company, or maybe if they intercept something from some other nation state, can we decompile it or just analyze the source code and find any extras, any backdoors, right? So about 2 years ago, we found that Huawei, the Chinese router company, kind of the US's equivalent to Cisco, was phoning home a whole bunch of extra data at the end of the nights, right? So there's something extra in that software, right? So we'd like a process where we can be reasonably sure that we'll find all the little extras added to the software. And what that boils down to is we need a precise tool to detect novel and sophisticated malware, because we're going up against nation-state enemies here, in advance. So how do we detect the 0 day before it happens, right? Before we even know there's a 0 day. So we spent a lot of money and a lot of time, about 2 years on this, and we learned that this is really, really hard, right? You don't just find malware. So what do you expect from this talk? Well, obviously I don't really have the answers. If you do, you guys are going to be rich. So this talk doesn't have answers, but it tries to step back and ask some fundamental questions about the problem. And hopefully we can start a discussion on what is malware and what isn't. So I think you guys have seen this example before, but I'm going to do it anyway. So a little icebreaker. Do you guys think that antivirus protects us from modern malware? What do you guys think? No? Okay, so a lot of no's. How about yesterday's threats? Sometimes, right? What about last year's threats?
Often.
Often, right? Okay, yeah, so confidence is going down. Oh, it's just totally worthless. Just don't even, right? Just why even run antivirus? Okay, well, there's not a really good answer, but there are some good answers, right? So here's a little exercise, and I think you guys went through this in a previous presentation earlier this year. So we take a 2-year-old Java exploit, and we just start refactoring it, right? We change the name of the class. We start just removing things. We obfuscate strings. We start to kind of pack it, compress it, just generally make it hard for static analysis tools to know what the software is doing, right? And within about, well, this took me 2 hours to do it manually, right? But a tool, all this can be done automatically, and it can be done randomly, so that every time you run the tool, you get a unique software, a unique piece of malware, right? But it's all logically the same. So we go through this process, and I went through this again for DerbyCon, and this time I actually decided to put a GitHub repo out there explaining all the little steps. If you guys want to go through and do this, you can go ahead and do that. But at the end here, we can get, so I ran this yesterday, and we got a 2-year-old, the same 2-year-old Java exploit, completely undetectable and still functional by all antivirus as of yesterday. So that, I'll show you the code real quick. Oh gosh. Okay. Presentation. So, okay. Yeah, so here's the code if you guys want to switch through, and I even saved the virus total links if you want to go back and actually see it. It's detectable in that. But what's fun is you start with the original pasty here. So this was the original proof of concept that got put out there. If you run this, hopefully you've updated your Java, or you're just not even running Java. If you run this, this won't work. So the way they fixed it was actually remove the vulnerable classes from the Java APIs. So if you run this, it's going to complain like this class doesn't exist, right? It's because you're running a more secure version of Java. But if you were running this in an older version of Java 6, it would actually launch a calculator on a Windows machine. If you change this to just calc instead of calc.exe, it opens up calculator in the Mac. So then we can, let's go back here. Okay, so the final version looks something like this. Okay, right, so we have all of our code. We've obfuscated it a whole bunch of times, and then we take it and we actually XOR it, so we kind of encrypt it with the weakest encryption scheme we can think of. We base64 encode it into a big string, and then the program that we run just undoes that, right? So it base64 decodes it, XORs it again to decrypt it, loads it into memory, and runs the class, right? And so this is not detected at all by any of the current antivirus. So the point of that icebreaker is really, this is not a solved problem by any means, right? Even, people with 1 or 2 years of programming experience could do this, right? Okay, so let's define what is malware. Okay, so if you just type define malware into Google, you get something like this definition. So I just kind of go by the definition that it's bad, malicious software, right? And that's just kind of this umbrella term for viruses, worms, trojans, spyware, ransomware, all that, right? Malware is just this big umbrella term. So what's also why we're at it, define a bug. So bug is an unintentional error, a flaw, some sort of issue in your code, right? And there's, all sorts of examples of that. Rounding errors, null pointers, these race conditions, business logic flaws, right? So, you forgot to check that this user has permission to do that action. So question for you guys, is a software bug malware under those definitions? Any thoughts? Yeah.
It can turn something into malware accidentally.
Yeah, right. So there's something to do with intention there, right? What if I added that bug? What if I worked for Microsoft and those bugs we just talked about? What if I was the developer and I added a bug intentionally that later, maybe I sell it to a bug bounty program or something, someone can now exploit it. So yeah, I would say a bug could be malware, right? But we have no way of telling the intention. From just looking at the code, we can't go and use rubber hose cryptography and just beat the answer out of the developer, right? Maybe we can. I don't know. Laws are changing. But so how do we determine the intention of the developer at the time? It's too hard to tell. So we have no practical way of discerning the difference between a bug and malware, at least in my opinion. Okay, so what do you guys think? A bug or malware? so a little context. This was found in the Linux kernel, the source code. And another hint, that line never executes. Ever. Yeah, I'm getting some downvotes. Okay, why is it malware? See it, Zach?
UID is set to use 0.
Okay, yeah. So there's a big difference between equals and equals equals. So equals equals in C++ compares the value of two references, right? So it looks like this code is saying something like, if the options wclone or wall, these are compiler flags. So when you run DCC to compile the program, you can give it some compiler options. So if those options are set and the user ID equals 0, what's the user ID 0? Root, yeah. So in Linux, Unix, user ID, the first user 0 is root, right? So if the user 0 returns some sort of error condition, right? But in this case, it doesn't check to see if it's 0. It assigns it to the value 0. And then in C, the value of the assignment is whatever the right-hand value of the assignment is. So this would return 0, which is always false in C. So that bottom line never executes. So if you're the attacker, all you have to know how to do is trigger this condition in the code, and now your root in the kernel, you have a nice, perfect backdoor, right? So there's a fun little story that goes with this and how they found it, but I'll move on. So can you guys see this one? What do you think? Bug or malware? Yeah.
Well, first on the last one, do you know if it was confirmed if that was a backdoor attempt? Or is
Yeah,
this
okay,
just-
so if you read the story, what happened was there was two repositories. Linux developers didn't like, some of the developers didn't like Bitbucket. They're like, we really like CVS, and CVS is crappy. So they had a CVS repository, and they had a Bitbucket repository. And every now and then they would go to the CVS repository and pull all the changes into the Bitbucket repository. It turns out someone hacked into the CVS repository, added this commit, and was hoping that eventually it would get pulled over to the main one. The way they detected it is every commit is supposed to have like a core developer sign off to say, yes, this is an approved feature. This one did not have that, right? So we're really sure it's malware, but we can never really confirm it. So we don't know who it was. We never caught whoever did it. So it was a sneaky attempt, but it was a failed attempt in this case. So yeah, okay, on this one. So there's a little extra go-to here. So go-to fail, does that ring a bell? Anybody remember that? So Apple had a go-to fail bug, and I love the name of that bug. They had a go-to label called fail, right? And go-to fail, I don't know, it's just ironic that that was the bug. But there's two go-tos. So that extra if at the bottom is completely dead code. In this case, that dead code is really important. This is an SSL certificate check. So, when you go to Amazon.com, the last check is that actually Amazon.com? Does their certificate check out? Everything's valid SSL, but does their certificate actually match, right? Well, that extra go-to there makes it so that last check is never actually checked. So for a year, I forgot how many it was, yeah, almost a year, iOS, MacBooks, all the Apple product line had this bug because it had shared code. And none of those were actually checking that the server they're connecting to was the server that they were connecting to. So pretty scary bug. Yeah, is that a bug or malware? A bug, I hope, maybe, but it's hard to believe that that's a bug. When you compile this with GCC, it spits out a warning. It says that's dead code. They indented the second one, so I don't know. It's hard to believe that that was a merge error. Merge tools don't normally make that bug, but who knows? Maybe, I don't know. I don't know who the developer was. I left. But, okay, so bug or malware. These are getting harder if you can't tell, right? The last one found with static analysis, really easy. In fact, the compiler tells you. This one, not so much. Okay, so another hint, more SSL. What was the other SSL bug this year? Yeah, Heartbleed, right? Okay, so this one's harder to understand. In fact, right before DeRecon, I spent like 2 hours trying to get this in my head to try to understand it. Basically what they do is they assign some macros, right? And these macros are populating the values of the array, allocating the size of the array. But in SSL, there is a feature called a heartbeat. And what that is when you're communicating with the server, maybe you're not going to do something for a long time, but you want to know that the server's still on the other end. So what you do is every now and then you send a heartbeat message. And to know that the server's on the other end, you say, please echo this message back to me so I know you're still there. And the way the SSL protocol works for the Heartbleed protocol is that you say, okay, I want to allocate I want to send a message that is this big, and you can send up to 64 kilobytes of information, and you'll get 64 kilobytes of information back. But the actual message that you send, that response that you wanted to be echoed back from the server, you can send a different length. They don't have to be the same length, and that's the bug. Because if I say, okay, the message is going to be 64 kilobytes, and I send just 1 byte, like the letter A, it copies that 1 byte into the array, and the rest of the array in C has a special property that, unlike Java, where the array would get all initialized, zeroed out, C is just whatever happened to be in memory before. So when it sends back, yep, here's your 1 byte message, and here's everything else that happened to be in my mind at the time. Right? So if we do this over and over again, we keep asking for information, and then we can just parse through the information and see what's in there. We can find all sorts of fun things, private Ssl keys, even easier to find that Matt Sullivan found from our group here was that you can find the session keys to your website, right? And we know from Cookie Cadger and the session hijacking that all we have to do is get that session key, and now I am you, even if there's SSL, right? Okay, so we also get this awesome logo. So first time ever we get like a cool logo for a bug. So I think that's a trend. So this one, much less obvious, right? Even when you're staring right at the code, it's hard to understand. Survived several code audits of professional cryptographers, right? And this lived for almost 2 years. The bug's actually a little bit older, it's like 2.5 years, but in production use it was actually out there live for about 2 years. So yeah, bug, I hope, right? If someone put that there, that would be awesome. It's scary, right? So people have all these theories of the NSA coerced someone or bribed someone to put that in there, but you know, we don't know. Also, it's rumored or alleged, right, that the NSA knew about this bug 2 years ago. So the bug's about 2 years old. So they knew about it for about as old as it was, right? So who knows what they were doing with this at the time? So right, that's why this was so scary, because everyone's like, well, who knew about this bug before we found out? It's been alive for 2 years. So all that information was potentially compromised. We have to change all of our SSL certificate keys. And that's expensive and a lot of work, right? So that's why everyone freaked out so much about this bug. Oh, yeah, and there's a follow-up study about a month or two ago. Still only about 1/3 of the internet of the vulnerable servers have patched those servers. So the other 2/3 are still unpatched. So pretty crazy. Okay, this one I had to add like the night before my presentation is what just came out, right? This one's really hard to see. So this one, the hint, there's initialize a shell variable there. So this is on the command line. So this was the shell shock button, right? And the issue here is that there's actually a lack of code. There's not code that you're looking for. The code just doesn't happen to be there. There's a sanitation check, right? You have some input, you define a shell variable. And what makes this one scary is when you define a shell variable, lots of applications do this. Specifically, web servers do this a lot. So when I make a URL request or I set your cookie and that goes to the web server, Apache just defines an environment variable, and then all the code like PHP can say, oh yeah, I can just look at the environment variable and get those values out. So to attack your server, all I have to do is craft a very special URL, right? And then I can do things like dump Etsy Shadow or you know, whatever I have permission to read on your system that your web server is running at. So pretty scary stuff. So this one is like complicated. If you don't see it still, don't feel bad because it took people 25 years to find this. Okay, so the fix adds some code. Yep, okay, so this one, like, how do you audit code that isn't there? You know, you have to think about what isn't there. You have to kind of put it together in your head. So 25 years, that's crazy, you know. Even more complicated to find. We're still kind of learning the extent of this bug. And now we get awesome logos for it. There's like a huge arms race of logos. I think the first top left one is going to win. And it's awesome. That logo has the bug in it. So pretty cool. So yeah, I think like whoever discovers the bug should get to make the logo, but that seems to not be the case because everyone's like, I'm going to make the logo. Okay, so last one, bug or malware. I know, everyone's confused. This is Java. I'd be confused if I had read the paper. Okay, so what are we doing? There's no method calls, there's no functions. All we're doing is defining a structure. We have class A, class B, and there's a bunch of it's just a funny looking structure, right? How could that be malicious? Well, this one's definitely malware. So what we do is we set up this structure in memory, and then we wait for a cosmic ray to hit our computer and flip a bit in memory, right? It's just a freak chance that memory happens to fail at that exact moment, right? But we're waiting for memory to fail. And once it fails, we can circumvent the type system because we've set up two classes, two types in Java, class A and class B, that once the bit flips, they'll be equal to each other. And that breaks the type system. So once you break the type system, there's some other research that we can actually write arbitrary code to the program address space. So in effect, we can run whatever code we want, right? But this is crazy. Like we assume our hardware is going to work and it's going to play well, right? But that's not the reality, and that's a really bad assumption to make. Because if we write software that just waits for that to happen, this paper did some research and they calculated that like once in a month a cosmic ray will hit in a way that this program could take advantage of that, right? So if I'm just a lazy attacker, I'm very, very persistent, I upload this, it just kind of runs for like a month just waiting. And then all of a sudden the right thing happens, a piece of hardware fails and we take advantage of it. So they set up this awesome like little test rig where they, another way to cause bit flips in hardware is through heat. So they just stuck a heat lamp like right on the processor and on the memory and just kind of waited and had some test scripts to actually do this. But you're able to escape the Java sandbox, which is a pretty crazy thing. Okay, so what's my point, right? I have to have a point with all this. So both bugs and malware, both of these have catastrophic consequences, right? Some of these bugs are indistinguishable from malware, like the Apple goto fail, like, you have to wonder a little bit. And that gives us some plausible deniability, right? So we can't tell the malicious intent just from looking at the code. And some of the issues can be found automatically, like the goto fail is another one, like the compiler warns us, but not all of them. Especially shell shock and Heartbleed, those are hard. I don't even know, what you do. Anyway, so, and then the last one, these novel attacks are really, really hard to detect, right? Everyone says like, oh, at a CDC, if someone throws a 0-day at you, you got nothing, right? They deserve to win, right? They found the 0-day. But the thing is, these bugs exist everywhere, right? So, why don't we just, I don't know. What are we going to do about that, right? So we have to do something about it because our adversaries are going to use those against us, right? We can't just throw our hands up. We have to try to address the problem. So we have a kind of a separation in the field right now. We have antiviruses looking for malware, right? Then we have all of these program analysis tools like Ssl, Coverity, that we write our code up, we try to audit it, we make sure that there's no bugs in it, and then we deploy it, we try to make sure that on the system, the integrity of all the programs is the same, but that's kind of hard to do in practice, right? But are we kind of doing ourselves a disservice by separating these problems? Because there is some overlap between the two of them. So what if, as the attacker, next time I compromise a machine, I just upload a vulnerable program? I don't upload malware in that sense. I upload a vulnerable program that I now know how to exploit later. Maybe it has a subtle buffer overflow issue, or a heap. I can heap spray the heap and take advantage of it. Maybe only probabilistically, maybe only 10% of the time it works, so I just do it a bunch of times until it works, right? Now I'm forcing antivirus to solve the problems of our program analysis tools. And that's scary, because I don't know what you do, right? Antivirus we've seen is terrible, so. Okay, so what can we do about it? Well, we have this growing infrastructure. The complexity of these systems, of all of our programs, is increasing, right? My Windows XP is, I don't know how many lines of code, and then 7 is even more, and 8's even more, and it's just like exponential, right? There's so much software just everywhere. And manual work's expensive. We have this kind of flip. Hardware used to be really expensive. You buy like a server mainframe from IBM, and we have one, and everyone would share time on it. But that's the exact opposite now. Now software is expensive. We pay our like starting software engineers like $60,000 a year, up to who knows what, right? And that's like your bachelor in software engineering. So it's a completely inverse problem now. So software is expensive, and it's too expensive to pay someone to go through all that software. But obviously we can't automate it all because we don't even know what we're looking for. How do you automate something that you don't know what you're looking for? So malware is this kind of cat and mouse game, right? Every time we learn a new attack, we try to write our tools to go back and find them. So the malware authors come up with a new attack, right, that we don't know how to look for. And we know we're terrible at finding bugs, so it's a bad situation. So really, we're kind of stuck doing manual analysis, but we need a tool that can make that human do manual analysis better and faster. And so that's where this cool thing from the Air Force kind of comes in. So Bruce Schneider's been talking about this a lot, and kind of follow Bruce Schneider, but I think he's definitely right on this. So you're not going to just buy a tool from some company and you're going to be secure, right? At the cyber defense competition, you secure the web apps, you secure all the little things they give you. You don't just run a tool over it and say you're done, right? You have to go through and you have to fix things, and you have to think about it. You have to think, how would the attacker attack me, and then try to mitigate that issue. So it's a process. You're not going to just buy a product. You're going through this process. And so OODA is something that came out of the Air Force by a guy named John Boyd. And OODA stands for Observe, Orient, Decide, and Act. So you're going through this feedback loop, this process. And it started with the Air Force, these fighter pilots, right? So you have two fighter pilots that are trying to dogfight. They're trying to outmaneuver each other and shoot the other guy down, right? So you have an attacker-defender situation, and one guy is trying to kind of observe, okay, there's a MiG here, right? He's flying at me, the Russian jet. Now I'm going to orient myself. So I'm going to synthesize that information and start to understand it. Okay, it's a MiG, so I know he can't take sharp turns. He can go fast, but he can't take sharp turns. So I decide what I'm going to do is I'm going to flank, I'm going to kind of make a really sharp turn. I'm going to get behind him. So I decide, and then I implement that, right? I act. And the whole point is we're trying to go through this loop fast, and specifically faster than the other guy. Because if I can do it faster than the other guy effectively, I decide and act before he can observe and orient himself. And in our case, we're trying to do this fast and well, and our opponent is time. Our time and also this evolution of malware, right? The attackers right now, the defenders are kind of really behind in this game. Used to be the other way around. Right now, the attackers have a leg up. So we have to get in front of them, right? We have to do this faster. We have to iterate faster, and that's really, I think, the only solution, at least in my opinion. So Fred Brooks was a guy that won the Turing Award, and his thesis was that artificial intelligence is always going to be less than a tool that amplifies human intelligence. So an intelligence amplifying tool is always greater than an artificial intelligence tool. So a human's always going to be smarter than a machine, but a human assisted by a machine is always going to win over everything, right? That's the trump card. And so that's kind of how we approach this problem from DARPA. So we developed a tool called Alice, which takes the source code or binary and indexes it. It creates this software graph, right? So if we can represent the code as a structure of information, we can now do some queries against it, right? So we represent the structure of the information, the control flow of the program, the flow of data through the program, which is something that like Pro is not so good at, but we're a lot better at. And then we can write programs that we can traverse these graphs and get responses. And there's a two-way correspondence between the two, so if you kind of interact with the graph, you click on the graph, you can see the source code, you can kind of go vice versa. So this is kind of what our environment works like. And DARPA is really focused on Android with the idea that anything we learn about Android, we can apply to a larger system, because Android is a nice, big, complex system. So it's good to just kind of focus on one thing in the beginning and then scale up later. So DARPA gives us these challenge applications, and we just went through this phase. They're getting incredibly hard. But what they do is they write a brand new Android application, a nice kind of cool application, and then in a couple of them, they add something malicious. And it's always novel. It's always a zero-day attack. So we get this application, and then the analyst has to either accept it or reject it, right? You're the App Store owner. You have to audit it, and will you let this into your App Store, right? And we can't just accept or reject all willy-nilly. We have to give some evidence, right? If we can't find anything wrong with it, we're forced to accept it. So we kind of go through this loop where we, index the software, create this program graph, we run some scripts against it, some questions that we can ask every single application. We learn something, we ask some more questions, and this is kind of iterative, hypothesis-driven approach, where eventually we've learned enough about the application that we can make a conclusion. Oh, oops, okay. So I had a demo of this. Let's see. Okay, so this was an app called Battery Indicator Pro. This is one of the early ones, so the malware is a little bit easier to understand. So what we're doing is just click this little I button up here, and that starts to index the source code, create that program graph, and now we can start to run our scripts against it. So these scripts are, like I said earlier, they're things that we can ask about any application. And so we might as well ask them anyway. Is this application calling some private API methods that aren't normal things to do? Is it using native code? Is it running commands on the shell? So Android has a little shell process too. You can actually, from inside the app, you can run shell commands. So is it doing things that look like it might be vulnerable to SQL injection? All those basic things we can just go ahead and run real quick. You see, it only takes a few seconds to kind of brute force through all those solutions. So we kind of separated it into the confidentiality, integrity, availability model. Also kind of properties and smells. A property is something we think the analyst should be aware of. Like, hey, it's using native code, we don't know what for. But a smell is something like really strong, like they're doing something really strange here. Okay, so this is a view we call the Android design context. But basically every activity, every screen inside an Android app, we want to see how does that connect to another screen or a service, or like if you receive an SMS, all these events in the Android operating system kind of tie together inside the application. So in this case, red are things that our analysis couldn't solve automatically because we might not have all the other information. There might be another application that interacts with it. In this case, we jump to the source and it's just like setting some device color preferences, like who cares, right? Whatever. So this next one's kind of interesting. If you know something about Android, what this does is it opens the default web browser with a URL. So what's the URL? When is this call from the program? We have some questions to answer. So we developed this thing called the Smart View, where we can ask really quick little questions like, we're going to switch to the call graph script here, which lets us see who calls this method in the code, right? So we click on the start intent method, we see that two other methods in the code actually call this method. So we jump to one and we see, okay, well the run is only ever called inside this background thread. And so to start the background thread, we have to call the object container constructor, which is only ever called by this other object container constructor, which brings us to another method called start intent, which happened to be right below the first one. So we're on this like wild goose chase already, right? But anyway, inside this method, we see something interesting. At the end of the URL, it adds a get parameter called data, and then there's some data. So now we have more questions. What is the data and what is the URL? So we switch over to following data flow through the program. And I just click on the URL variable there, and then we get this graph on the right side. So we see there's actually 3 values that this could possibly be, but at the end there's one that gets overwritten inside the method. So we just click on that, we jump to it. So we see that the URL is this myserver.test.com. Now DARPA always takes the teeth out of all the malware, so this is supposed to represent like a malicious URL. And now the data that gets passed to it is in this update URL value here. So let's go check out that method. And the method here, you just kind of glance at the source code real quick. We see that, okay, there's something to do with the camera directory pictures, and it's hex encoding, right? So I have enough pieces in my head now, okay. It's using the browser to upload a URL, and the URL contains my camera information. What's going on here, right? And it's using the default web browser because this application doesn't have permission to connect to the internet. So it asks another application on the system to do it for us, which is why we couldn't automatically solve this, right? We already know, here's all the places it can connect to the internet, but if it asks a different application to do it, well, that's tough. That's hard to do automatically. Okay, so in that case, we had source code. In the beginning, DARPA said, yeah, you'll have source code with us, and easy, no big deal, right? But it turns out it's really hard. A second video. Okay, so that one's kind of fun, right? It's short, it's easy, but they're not all that easy. So here's another one. This one took me 12 hours to solve. And I magically just happened to have enough persistence to find it on this app and also record it. So here's a time-lapse video. Each hour is 1 minute. And so what I'm doing is I'm just trying to go through this application, and I'm using this tool to try to get an understanding of what the application does. So this application was a tool that, an Android application that was basically Nmap. So it would scan network computers, and it contained a custom compiler that was written in Java that would compile a custom programming language that they invented just for this application. And in that custom programming language, they wrote a piece of malware that goes out to the SQLite database inside the application, fetches 15 different rows from the database, assembles them in the virtual memory of the custom programming language, and then if it happens to be a Windows computer on your network scan, sends this malicious exploit over the network to the Windows computer, right? So this took me forever, because I'm not even auditing Java anymore. I'm auditing a custom language inside Java, right? So I'm really just using this tool to get a better understanding of what the code is doing, right? So I'm doing a manual process, but I'm trying to do it faster, right? And so our team, we found this malware. There's only one other team that found this malware in the challenge. We're going up against MIT and Stanford. But we found this malware in half the time that the other team found it. So we were super excited about that. So it's not just can you find it, but it's how much effort did it take you to find it. Okay, so finally, so that's source code. So what about binary? Well, we can do binary too. And the way we do it is we take a binary, we compile it to some intermediate representation, so an intermediate language. In this case, we use Jimple when we convert from bytecode. And then we can index that intermediate representation to create the same program graph. So we can reuse all of our analysis scripts that we wrote for the source code to analyze a binary program. So I want to demo a piece of malware that was found in the wild, not by us, but I decompiled it and got all the source. So what this did was, it was a comic book. No, sorry, not this one. This one's not a comic book. But this one was, there was a phishing email that said, like, you have to complete your tax forms or whatever, and it was sent to email addresses that the attacker, for some reason, thought were mobile devices. Anyway, in this link, it says, like, oh, you would go to this web page and it would say, oh, you have to update your Flash player on your mobile device. And so it links to this Android application, which looks like a Flash player update, but is everything but. The only thing that has in common with a Flash player update is the name and the icon. Everything else is just complete. It's all the code is malware. So it can download and execute files. It's basically like one of the first little mobile botnets. That's why this app got so much attention. But it steals your contacts list, can send SMS messages, connects to a server, and waits for commands, can uninstall apps, can show notifications, all sorts of fun little stuff. And one of the first things it would do was it would sign you up for a premium SMS messaging service, kind of like Catastrophic or something. And the attacker would control this premium SMS number. And then what he would do, so that you wouldn't know, is he would intercept all your text messages from that premium SMS number and just throw them away, so you would never get them until at the end of the month when you get a huge bill. Right, so I want to do a live demo, so we'll quickly phrase the demo guys. Okay, good enough. And we're going to import this malware skills, and we'll browse to desktop. I have way too many things on desktop. Okay, we're going to decompile that Android application. Go, no errors, no errors. Yes. Okay, we're going to index that source code of the Android application. And so as indexing, we can look and see kind of what we get. Not quite Java, but it's not quite like bytecode either. It's kind of a mix between. So here's the base64 encoder class. So it tries to encode and encrypt all its commands with like a really funny XOR thing. But yeah, so there's no for loops or while loops. You all have a bunch of go-tos and labels, but you still have the type system. You still see, oh, it's a Java string. It's, here's a character array. So it's not too hard. You could just sit there and read that if you wanted to. Okay, so I'm going to go ahead and apply our permission analysis, which basically looks to see what permissions are called by the application. So not only what permissions is the application requesting, but what permissions is the application actually using. So we can kind of get a good idea here. So read phone state lets you get the SIM card number, which is scary because from the SIM card number you can actually get someone's billing address. We can send SMS messages, we can connect to the internet. Yeah, let's see. Let's go to where it gets the SIM card number. Okay, so the subscriber ID. Oops. Oh God, I opened the door. Okay. Okay, so we get the subscriber ID. We can see. Oh, it stores it in. Oh, okay, it's getting the phone, subscriber ID. There's some other stuff up here. Yeah. Okay. So I don't know. It's getting subscriber ID. Who knows what? But we can actually run all of those automated analysis we have against the script. So here's one that looks to see does the application eat incoming text messages. And we see that it actually does here. So it calls the support broadcast method when it receives an SMS message. Yeah, so this application does all sorts of bad stuff, and our toolbox just kind of lights up the whole thing. So it seems like analyzing stuff in the wild is not too hard because they're not really trying to hide. Let's get back on track here. Okay, so I just want to end the presentation with kind of a fun thought experiment. So consider a spell checker, right? And what happens if you just inverted the spell checker's logic, right? So instead of correcting words, it like uncorrects words. So you get what I call a spell wrecker, okay? And so if I gave you a spell checker and a spell wrecker, how would you automatically kind of tell which one was bad, right? Without having some sort of kind of human in that loop trying to understand it. I don't know. It'd be difficult. But anyway, so I actually wrote this if you want to like play with it. And I added some extra little fun features. So it's not a keylogger, but it does pay attention to how fast you're typing. So does Microsoft Word too, by the way, right? If you type like naive really fast, it's like, oh, you probably meant the other way around. Actually, I use, yeah, I don't know. Anyway, so this one, as you start to approach your fastest typing speed, it actually starts introducing subtle typos, kind of based on like your keyboard layout. And as you slow down, it starts to behave. This would be kind of a huge headache, right? So there's lots of fun ways to inject this. We can actually compromise the Java virtual machine pretty easily, and so we would affect every Java application on the box. We can do this with C#, any .NET, any of the runtime systems. So things like C#, anything that runs in a virtual machine. But the better thing to do would be to kind of put this kind of blended in with legitimate functionality, right? So if you had like a keyboard app on your phone or like Microsoft Office, if we could like blend it in there and make it look like a spell checker, right? That would be really evil. Okay, so hypothetical malware is the last one. So believe it or not, cars are becoming drive-by-wire. So we've heard of fly-by-wire, like the plane has some autopilot, right? It tries to stabilize the plane. But cars are doing this too. And they have a thing called the electronic stability controls, ECS, I think you've also heard of it, like ESP, not ESP, it's a different thing. But anyway, they're adding them to SUVs, specifically like SUVs, vans, trucks, things that have a high center of gravity. Because what happens is when you shift lanes at highway speed, you have a kind of a higher chance of rolling over, right? And that really kind of negatively affects the car's safety rating. And that's bad because you lose kind of financial profits, right? So what they do is as you shift lanes, it's very subtly actually individually braking all four of your tires in a coordinated fashion so that as you're shifting lanes, you have a lower chance of rolling over. So what happens if we took that algorithm and we inverted it, right? We have like a cyber D-Day, all of a sudden all the like Toyota or Japanese cars like roll over one day on an afternoon at 12 or something, right? So, how would we, it's the same problem as the spell record. How do we like automatically detect the difference between the two? And it's worse because there's actually all sorts of really evil ways that we could implement this and look like we're doing a good thing. So greedy algorithms are like kind of the first algorithms you learn in like Comp Sci 2.7, 2.8, your first intro to the Comp Sci courses is imagine like the traveling salesman problem, and each iteration you try to just take the best looking option, right? But there's a property of greedy algorithms that under certain conditions, they always take the worst possible outcome. So what if I implement it as a greedy algorithm, someone's auditing the code, they're like, yeah, that would work, it seems like it'd work. It's the first algorithm that comes to mind, it's totally believable, but elsewhere in the code, I set up the conditions so that it always fails in the worst possible way, right? So anyway, legitimate bugs are hard enough to find. How are we ever going to find the illegitimate bugs? That's kind of how I ended my talk. So if you guys like the Atlas stuff, you can actually get a free academic license. And the binary isn't there yet publicly, so go ahead and request a copy of Atlas, and then at the bottom say like, we want binary. So yeah, if you guys have any questions, shoot me an email. But otherwise, I got to run. I got like 4 phone calls in the last minute. So. Okay, so thank you guys very much for letting me present to you. And I also recorded it, so there is